Welcome to This Explainer. You know, if you've ever watched a large language model spit out a massive paragraph of text and thought to yourself, wait, how on earth do we actually measure if this is any good, or if the AI is just confidently hallucinating alphabet soup, well, you are in the exact right place. Today, we're demystifying a concept called perplexity. Now, I know it sounds like a super complicated, dense academic term, but it's actually the absolute bedrock of how we evaluate the AI tools that we're using every single day.
So let's just dive right into the core definition. Perplexity is basically a metric that measures the uncertainty of a model's predictions for the next word. Think of it kind of like the ultimate autocomplete analogy. When your smartphone tries to guess the very next word you're typing, sometimes it has a dozen terrible guesses, right? But other times, it knows exactly what you're going to say. Well, in language models, a lower perplexity means the model has lower entropy. Essentially, it has fewer choices on the table, and it is highly confident in its next guess. It represents the literal number of potential options the model is considering in that exact split second.
But here's the crucial point. Why does this actually matter outside of a sterile computer science lab? Well, if we're building or relying on massive AI systems, things like GPT-3, we really can't just cross our fingers and hope they speak fluently. We need a concrete, quantifiable way to evaluate if they are predicting the next token effectively or if they're just completely lost in the statistical weeds.
So here's our roadmap for this explainer. We're going to peel back the layers on this. 1. What is perplexity? 2. The math behind the metric. 3. Evaluating LLMs in Python. 4. The good and the bad. And 5. Real-world AI applications.
Section 1. What is perplexity? Let's officially define this metric.
We can really break the why down into 3 core functional pillars. First up is prediction accuracy. A low perplexity score means the model is highly likely to generate coherent, fluent text. Second is confidence. And listen, a high perplexity is a massive red flag. It signals that the model is uncertain, and that almost always leads to totally incoherent babble. And third, evaluation. By tracking this metric, developers can definitively decide if a language model is actually suitable for complex tasks, like text generation or machine translation, before rolling it out.
All right, Section 2, the math behind the metric. Let's calculate that uncertainty.
To actually get to that final perplexity score, the mathematical engine under the hood has to go through 4 sequential steps. Step 1, prediction of the next token. Basically, the model assigns base probabilities to the very next word based on the input text. Step 2 is a logarithmic transformation. We take the log of that probability, mostly because it transforms these insanely tiny probability fractions into a much more useful, manageable number. Step 3, we compute the average log likelihood of all the predicted words in our entire test set. And finally, step 4, exponentiation. We simply exponentiate that average log likelihood, and boom, we arrive at our final perplexity score. Now, if you look closely at the underlying formula here, notice that exponentiation right at the very beginning, wrapping around the average log probabilities. But honestly, the absolute most important takeaway from this equation isn't memorizing the symbols, it's understanding the output. This formula essentially tells us how many words, on average, the model is currently choosing from. So, a lower perplexity indicates fewer choices, which means the model is much more confident.
Section 3. Evaluating LLMs in Python. Let's look at the implementation.
If you actually wanted to implement this yourself to evaluate a pre-trained model, the Python workflow is beautifully straightforward. First, you just import your required libraries. Second, you load up a pre-trained model and its tokenizer. Third, define a custom function to handle that exact math we just talked about. And fourth, you just run it on a batch of test inputs.
Looking at those first 2 steps, we import Torch for tensor computations, along with the transformers library. What's absolutely vital here is loading that specific GPT-2 model. Also, pay close attention to that last line of code, setting the end of sequence token as the padding token. Actually, don't skip that, because that step is critical to ensure the model processes padding correctly when you're evaluating texts of different lengths.
Okay, let's look at a practical contrast when we actually run this evaluation. We fed the model 2 different texts. Text 1, once upon a time, there was a brave knight. This received a score of 25.61, indicating, moderate uncertainty. But then text 2, in a galaxy far away, a new adventure began. This received a significantly lower score of 18.61. That lower score literally means the model was far more confident predicting its next words. It had way less uncertainty navigating a galaxy than it did our brave knight.
Now, a single score is cool and helpful, but evaluating a whole batch gives us a mean perplexity score, like this 22.11 right here. By averaging the scores, developers get this rapid, overarching sense of the model's performance across multiple, totally diverse inputs, rather than just trusting one single lucky sentence.
Section 4. The good and the bad. Let's cover the advantages and limitations.
So perplexity is incredibly powerful, which makes it a massively widely used metric in the AI industry. But we have to be honest here. It absolutely does not tell the full story. We've got to talk about its limitations.
Let's objectively weigh this out. On the pro side, it is highly intuitive. It literally translates a model's invisible mathematical uncertainty into a format we can actually read. It allows for lightning-fast real-time evaluation during training, and it's fantastic for checking your progress while fine-tuning. But take a look at the cons. Crucially, a low score does not measure understanding. An AI model can confidently predict a completely fluent sentence that is 100% irrelevant or factually wrong. Furthermore, Perplexity really struggles to capture long-term dependencies across massive sequences of text. Oh, and it's highly sensitive to tokenization. For instance, character-level models might show a lower perplexity than word-level models, but that doesn't necessarily mean they're better at generating coherent text. You simply can't compare apples to oranges.
All right, Section 5, Real-World AI Applications. Let's look at some practical scenarios. When you look out into production environments, Perplexity is quietly working behind the scenes literally everywhere. In text generation, it ensures the model's outputs actually make sense. In machine translation, it assesses exactly how well a model predicts the very next word in a completely different target language, which ensures high quality. For chatbots and virtual assistants, maintaining that low perplexity guarantees the conversational responses flow naturally and don't suddenly glitch out. And in summarization, it guarantees the generated summary stays tight and highly readable.
But remember that huge limitation we talked about earlier? It does not measure truth. And this leads us to a critical best practice, using perplexity alongside other metrics. To build truly reliable AI, perplexity has to be just one part of a much broader toolkit. We absolutely have to combine it with metrics like Blue or Rouge for translation, diversity scores so the AI doesn't just endlessly repeat itself, factual accuracy frameworks to stop wild hallucinations, and crucially, human evaluation to catch all those subjective human nuances. Put simply, perplexity tells us if the AI is confident, but these other metrics tell us if the AI is actually right. Which leaves us with a pretty massive question to ponder as we wrap up. How might you combine the raw mathematical confidence of perplexity with the subjective, nuanced reality of human evaluation to build safer, more reliable AI? I mean, if mathematical certainty is really just one piece of the puzzle, how do we best bridge that gap in the real world? Thank you so much for joining me for this explainer. Keep questioning the metrics behind the models, and I'll see you next time.